Well, thanks very much, and thanks very much for inviting me here and giving me this opportunity to speak twice even. Can you hear me in the? I'm not sure if this microphone is really. Oh, I see. Yeah, I get the go-ahead sign from the very back. Yes. So as Anish said, I'll speak about logical approaches to graph algorithms. So I thought, since this is a workshop on logical approaches to barriers and complexity, I should speak about something related. And so the motivation for it's working. This talk is basically what we want to look at is the role logic can play in the design or the analysis of graph algorithms, basically. Right, so we are interested in standard computation problems in graphs, such as finding a dominating set, which is a minimum set of vertices, so that every other vertex is a neighbor of the dominating set. Or three colorability, where we want to color the vertices of a graph by three colors, so that no edge has both endpoints colored in the same way. Or the Hamiltonian path problem, where we want to find a path containing every vertex exactly once. Right? So it's a path and it contains every vertex. So these are just three examples for standard graph theoretical problems that we want to solve on graphs, and they are all very well known to be NP-complete. So we don't normally expect, well, I guess most of us expect that there won't be any efficient algorithm solving them on all graphs. I know a few exceptions. Right? So what people have done in an area you could call algorithmic graph structure theory is to look at sort of more restricted classes of graphs, like planar graphs or graphs which look like trees in some sense, and so on and so forth, and then try to find efficient algorithms solving these problems on these specific classes of graphs. Right? And normally, well, the most prominent examples of classes where that have been studied come from graph structure theory. So I mentioned planar graphs or tree-like graphs, and you'll see exactly what I mean by this in a few moments. But we also have the graph class excluding a minor and of boundary expansion and so on and so forth. So all these things that are studied in graph theory. And so here's a little diagram which in variations you'll see quite a lot in this talk. I don't expect you to know all these classes on the diagram here. It's just to give you some idea of how these classes relate to each other. So I guess trees is the most basic class, and I guess common assumption is that nearly everything is easy on trees. Right? And then from trees we can generalize in various directions. One is to go to planar graphs, which are graphs you can draw on a blackboard without crossing edges. Or we can go to we try to keep tree likeness, and then that's formalized by bounded tree width, and I'll explain what this is. And then we can go to larger and larger classes of graphs. So here's another sort of special case is bounded degree graphs, like this, and then you go up. So here are class excluding a minor and something else we'll see later on, and so on and so forth. So don't worry what they are exactly, just we have a whole hierarchy of classes. And so what we would like to do somehow is to study the problems I mentioned before and all these graph problems on restricted classes of graphs and see where they become tractable. And so it's known that on bounded tree width graphs, Hamiltonian path can be solved in linear time actually. And then three colorability we can solve in slightly larger classes of graphs, which are called bounded click width. I'm not going to tell you what this is. And if you go up for problems like dominating sets, independent sets, cliques, and so on, then we can solve them way up here, up to Norwood dense classes, which is sort of currently the largest class studied in this sense. But what you see, we know that all these problems are hard, right? So on general classes. So somewhere, if you take dominating sets and you study where you can solve them, at some point you will have to sort of hit a complexity barrier where you can't go further, right? Because we can't solve them efficiently on the class of all graphs unless we solve P versus NP. In the unexpected direction. So at some point we'll sort of hit the boundary. And so what people in this area are working on is they try to explore this tractability frontier for various problems. Right? And this can be done in two directions. So one is we study one particular class of graphs like planar graphs, and then we try to figure out what kind of problems we can solve on them. We try to sort of improve the algorithms doing so and get better running times, practical implementations, and so on. And the other areas that you can look at is you look at certain problems like dominating sets, and you try to explore how far you can solve them on what type of graphs and so on, give you sufficient structure to solve them efficiently. Okay. And so this is more the sort of the kind of area where logic can help actually. Right? So in this programs, thousands of papers have been written and so on and so forth, and So much research has gone into developing specific algorithms for certain problems on certain graph classes, and then you improve them and so on. But if you really want to understand the complexity barriers that we have to face in sort of general problems like dominating sets and so on, I think sort of more general results are very useful. So results which you could call a meta theorem that give you sort of tractability results for a large class of problems in one go. Right? So results of the form where every problem satisfying a certain criteria all problems satisfying certain criteria are tractable on all graphs satisfying a property P. Like every problem that has some property to it, you can solve in planar graphs would be a good example of this kind of things. And these results are known, and they come in very different flavors. One is the more algorithmic approach that sort of the graph structure theorists would design. And this is one example, a theorem by Demain, Hajiagai, and Kawarabayashi in 2005. It's not really important what it says, it's just meant to give you a flavor of these type of results that these guys are proving. So here they specify minimization problems, so we want to approximate problems like dominating sets. And the theorem says, well, if you can solve your problem in polynomial time on graphs of bounded tree width, which we'll see in a moment, and further on you have these two algorithmic conditions. So if you split a graph in two parts, then sort of the optimal cost doesn't increase too much, and the value sort of sub-solutions in the two parts you can combine efficiently somehow. This is roughly what's saying here. And then they prove there is a polynomial time approximation scheme for this problem on any class of graphs excluding a fixed minor. Right? So basically, whatever this theorem really says in detail, what they're doing is they give algorithmic criteria to your problem, and if you can sort of provide these algorithms for solving these subcases here, then they give you an algorithm for solving this problem or approximating this problem on a certain class of graphs. Right? And this is, of course, very useful and nice. It means you have to sort of work algorithmically on your problem. You have to understand its algorithmic properties. And that's not so much my sort of cup of tea, if you like, at least not in this talk. And therefore, I want to use a different, and I think not less elegant approach, which is based on logic, a descriptive approach. Right? So, and we use the fact that many problems, so many natural problems can also be described very naturally in an easy mathematical way. So if you think of dominating sets, then of course there's a very simple first order formula that says of a set X of vertices that this is a dominating set. You just say every element Y is a member of X, or there is a member of X which is a neighbor of Y. And if you're more interested in decision problems, for any fixed K to decide whether there is a dominating set of K vertices, you can formalize the first order logic in a straightforward way. Right? The same for three colorability. This is no longer first order definable, but it's definable in logic called monadic second order logic that I'll also define in the next couple of slides. So three colorability can just be naturally expressed in this formula saying you have three colors. Every vertex is contained in a color. And whenever there's an edge between X and Y, then X and Y must get different colors. Right? So that formula would be true in a graph if and only it's recolorable. Yeah? And the same for Hamiltonian path. I mean, okay, here I'm treating it a tiny bit. You can easily say in a variant of monadic second order logic that there is a set of edges forming a path, and then every vertex is contained in that. Right? But even if I wasn't cheating, this is not a complicated formula. Right? So basically, good problems are definable easily in natural logics we all know. And so this gives the idea that we maybe use this logics to describe problems and then try to get general algorithmic results by logical formulations. Yeah? And so the type of results I'm after is one we proved a couple of years ago. So with Anush and Nicole and Martin Groh, where we proved that every minimization problem, such as dominating sets and so on, that is definable in first order logic, this has an efficient polynomial time approximation scheme on any class of graphs excluding a fixed minor. Okay. And so if you compare this to the previous theorem, they basically give very similar results. Only here, what we require is that the problem is first order definable, so describable in a language we understand. And here, you don't need to show first order definability, but you have to give algorithmic criteria. Right? So they come in two different flavors, and obviously both have advantages and disadvantages. And in this talk, basically, I'm interested in theorems of this form. So theorems that more generally say every problem definable in a given logic L is tractable on any class of graphs satisfying a certain condition.
The other difference is the efficiency.
Yeah, we are more efficient, that's true.
In what sense, can you say?
Sorry?
Can you
Well, the efficient means, a peak just means for every error ratio epsilon you're giving this is a polynomial time algorithm. And efficient just means the running time is a fixed degree polynomial, and then there's some exponential depending on epsilon.
So the uniformity?
Yes. But yeah, okay, I'll stop there. I mean, I could say more about the running time we obtain, and then the efficient would be questionable, but somehow I remember actually you asking in the talk, Alex, what the running time was, and it was a bit dodgy, but yeah. Anyway, yes, but I didn't really want to go on the efficient. I mean, I guess you could also prove it's an algorithmic version that gives efficiency, but here we go. So the difference is really in the flavor we don't want algorithms I want to describe. I mean, I view logics here as a kind of high-level descriptive programming language. You express your problem, and then sort of the computer solves it for you on these classes. That's the idea. And so results of this form are usually referred to as algorithmic meta theorems, which is because they were first developed in logic and then gave algorithmic applications. This is where the name comes from. I guess the algorithms people would love to call it logical meta theorems, but it's now too late. And I think the main advantages of these kind of theorems is, well, in one go they provide a very a uniform explanation of tractability for very natural classes of problems like those definable in monadic second order logic. And by doing so, they also establish very general algorithmic techniques that you can use to solve all of these problems, right? So we'll see one for monadic second order logic on bounded tree with graphs, and that gives one algorithm to solve this every problem defined in the logic, and so we have a uniform explanation and a uniform technique to doing so. And also, tomorrow in the second part of the tutorial, we'll see corresponding intractability results. So results that say if your class of graphs does not have bounded tree width in some form, then MSO is no longer tractable. And by doing so, we also exhibit very natural boundaries, sort of complexity boundaries beyond which you can't push sort of these type of problems. Right? And basically, the purpose of this, the topic of this talk is to survey well, about 10, 15 years of research sort of focusing on these meta theorems. Right? But before I'll do so, let me rephrase everything I've just said in logical terms. Just to make it more precise. So if you take away all these sort of algorithmic motivation, what we are really looking at technically is the model checking problem for a given logic L on a certain class C of structures. So the problem, you're given a finite structure as input, and because there's so many infinite model theory and proof theory people here, so everything in this talk will be finite, every structure and so on, even if though I'll probably forget to mention all the time. Yeah, so we have a finite structure as input and a formula from our logic, and the question is the formula true in the structure? And by formula here, for simplicity, I don't consider any free variables, so it's just a sentence in this logic. Yeah. And so algorithmic meta theorems in this terminology can just be rephrased as a problem. We fix a logic L we're interested in, such as monadic second order logic, and then we want to understand on which classes C of structures this logic becomes, the model checking problem for this logic becomes tractable. And the logics we study is first order logic and monadic second order logic. I assume you know what first order logic is, but MSO comes in various flavors, and so I'll explain briefly what this logic is. So monadic second order logic is just the extension of first order logic by quantification of a set of objects. So we have existential and universal quantifiers like this. There is a set of objects satisfying the formula phi, or for every x, set x, there's the formula phi is true. And then we have the normal formula building rules of first order logic, so we can quantify over elements, and we have Boolean connectors, atomic formulas, and so on. Right. And so in the language of graphs, where E is just the edge relation of a graph, this formula that you've seen before actually says that the graph is recoverable, right? And we've seen this formula before expressing it, right? Oh, no, it works actually. Yeah, but there's some subtlety in how we encode graphs. As a graph as such is just a set of vertices and edges between them. So to use logic, we have to somehow encode this as a logical structure. And there are two different ways of doing this. One is the standard encoding, where the signature just contains one binary relation predicate corresponding to the set of edges. And then the graph is just a sigma G structure. Vertices are the universe, and then we have a binary relation. The other way of doing this is called the incidence encoding, where we are basically working on a two-sorted structure. So here the signature contains two unary predicates v and e, and the binary one, the incidence encoding. And then the graph G is just encoded as such a structure where the universe consists of all vertices plus all edges. And then V is just interpreted by the set of vertices, E is interpreted by the set of edges. And then the incidence relation says that a vertex S, X is contained in the edge E, right? And that's the second sort of relatively straightforward encoding of the graph. Well, there's a huge difference between these two encodings if you use monadic second order logic. Because here basically, since in MSO we have quantification over sets of elements, now here in this encoding we can actually quantify over sets of edges, right? And so over the incidence encoding in MSO we can say there is a set of edges which forms a Hamiltonian path, which you cannot say on the standard encoding, right? And so MSO has very different and in fact vastly more expressive power over this encoding than the standard one. And therefore, whenever I'll speak to monadic second order logic on the incidence encoding, I'll call this MSO2. And if it's, basically this is quantification over sets of edges, and MSO1 just refers to a monadic second order logic on the standard encoding. Right? Yeah?
How do you prevent having multiple cycles in your path?
Sorry?
I'm probably just missing something simple. How do you prevent having multiple cycles in your path P?
Well, you have to express this, right? I mean, you say there is a set of, so what do you say? There's a set of edges. This forms a connected subgraph that you can express, right? So you don't have disjoint.
Because you got more existent. Okay.
There's a lot hidden here. I mean, this is not just a simple atomic. No, this is certainly not first order.
Okay.
Yeah. No, good point. You have to use connectivity, right? Which you can express in monadic second order logic. But connectivity is actually definable even sort of in the standard encoding, but you can't quantify over. The main difference here is that you can quantify over a set of edges and then say that this forms a connected subgraph containing every vertex and it's acyclic and so on. But in MSO1, this would be doable basically, but you can't quantify over the set of edges, right? And obviously, if you want a Hamiltonian path, it makes no sense to quantify over the set of vertices in this path because that's just everything.
Right. It's not purely existential MSO?
There's a universal quantifier in here. Yeah, this is hiding a lot. If you really, it's not super difficult, but it's more than there is. Right, but the bottom line is MSO1 and 2 are really two different logics when it comes to expressive power, and we'll see this they are tractable on different types of graphs.
It bothers me because it seems such a, this shouldn't matter somehow. And somehow I think we're missing something, some people theory here that would somehow enable us to smooth away this difference in between coding.
I'm not so sure because, I mean, if you quantify over sets of edges, it means you're not going to induce subgraphs in the sense, right? I mean, take the class of cliques. If you can quantify over edges, you can quantify basically over every graph you want in your clique, right? Because everything is there, so you can quantify whatever you want. In fact, tomorrow I'll prove that provided complexity theory doesn't collapse as we know it, these two logics really are different, right? Because MSO1 is solvable on bounded clique width graphs and MSO2 isn't, right? But there may be a more uniform approach to this. But the second answer to your question would be, I think it's just presenting it this way is easy because it fits on the slide, but it's not the right way of doing this somehow, right? So the real difference here is that MSO1 is just MSO as it should be, and MSO2 is guarded second order logic, right? So it just comes as a disguise that all the guardedness is coded in the incidence encoding, right? But really I should be speaking about guarded second order logic. It's just a nuisance to define. Yeah, so for those of you who know guarded second order logic, this is exactly MSO2 when you work on graphs. Okay. All right, so complexity of model checking problems. This is what we're talking about. So let's first briefly review the sort of classical complexity of these problems. As I said, we are given a finite structure which always will be a graph in this talk, but nevertheless, and an MSO formula, and we want to decide whether the formula is true. Now, the most naive algorithm is just brute force, right? So whenever you follow the structure of the formula from the outside in, whenever you see an existential second order quantifier, you try all subsets, as witnesses. Whenever you see a first order quantifier, you try all witnesses, and then Boolean connectives, you do what you have to do, and once you're at the atomic level, you just look this up in the structure. Now this naive algorithm runs in time for monadic second order logic, basically exponential in the formula, which comes here from this existential, the first order quantification, and also exponential in the structure because you have to check all subsets. And the space consumption is linear both in the formula and in the structure. For first order logic, this is easy because that case can't exist, right? So you basically drop an exponential in the size of the structure, so it's only polynomial time in the structure and logarithmic space in the structure. Of course, this is the most naive algorithm, so maybe we can do better, but it was proved that, actually I hope this number is right, I wasn't sure, that we can't do much better. So first order model checking is p-space complete, and MSO model checking is equally p-space complete. And this follows from a straightforward reduction from quantified Boolean formula problem. Right? In fact, this even holds true if you fix the structure on two elements. The two elements would be the truth values, and then you can just reduce Q by F to these problems. So this is not so good, and therefore sort of, well.
Is even true applied to what? Yeah.
Sorry?
This is even true applies to what?
This is even true brackets for a fixed two-element structure A that we take in the model checking problem. So expression complexity, let's say. Yeah. Yeah. Okay. But then, of course, somehow, I mean, if you think of the original motivation, like expressing Hamiltonian path in MSO2, then basically the formula is just like the program code, right? Normally, you wouldn't take the size of the program code into account if you analyze an algorithm somehow. So we shouldn't be doing this. And in the same paper, I think the notion of data complexity is studied, where we study a model checking problem, but we fix the formula, and that's not part of the input. Only the structure is part of the input. But then again, there are MSO formulas like 3 colorability, obviously, which express NP-complete problems, so they are NP hard to evaluate. For first order logic, the situation is better. If you fix the formula, then the problem becomes solved in log space. In fact, even as we heard this morning, in AC0 more or less, certainly in polynomial time. But this is also not extremely nice because the running time here, the degree of the polynomial is basically the size of the formula, a bit less. But and you'll see later we are mostly interested in parameterized complexity, and this kind of running time is too big for us, right? So we want to do something else. But despite this high complexity, it is also known, and this follows from classical work by Büchi and Donner and Thatcher and Wright and various people sort of in the 60s and 70s and so on, that for every fixed MSO formula, deciding whether it's true in a given tree, in a finite tree, can be done in linear time. Right? You translate the formula to an automaton, and then that runs on the tree, and this is a linear time procedure. So in other words, the model checking problem for MSO on trees can be solved in time, well, f of phi, where f is any rather bad function, but then only linear in the size of the tree. Yeah? And hence, by restricting the class of admissible inputs, we can achieve much better running times. And this is exactly, of course, the type of problems we are looking at, because we want to restrict the class of input structures to, say, planar graphs and then get better algorithms. And so to analyze the complexity of model checking problems in this sense, it makes sense to look at parameterized complexity, a complexity framework introduced by Rod Downey and Mike Fellows. And and so the key notion here is the notion of fixed parameter tractability, where we say a model checking problem is fixed parameter tractable if it can be solved in this type of running time. So if it's any computable function, so we can spend as much time as we want in the size of the formula, but only fixed degree polynomial in the size of the structure. And I think Rod is actually just walking down in 2 seconds. He missed his slide. Yeah, and this type of complexity has been studied a lot in graph algorithmics. So similarly, problems such as the dominating set problem is called fixed parameter tractable on a class of graphs. If on input the graph and the size of the dominating set we are looking for, we can solve this in time f of k times the fixed polynomial in the graph. Right? So it depends badly on the size of the dominating set we are looking for, but only fixed polynomial on the size of the graph. And so people in this area want to sort of find this kind of FPT algorithms for problems that make sense also for us in a logical approach to look at parameterized complexity. And so the complexity class, that's basically the role of P in parameterized complexity, is the class FPT of all fixed parameter tractable problems. And then there's also an analog of NP, which is a hierarchy of classes called W1, W2, and so on, but we don't really need this for the moment. Okay, so this is the framework we work in. And so the very last rephrasing of algorithmic meta-theorems, and then I'll actually prove a few, is the following. Basically, we fix the logic, and then we're interested in the question, what are the largest or most general classes of structures where the model checking problem for this problem becomes fixed parameter tractable. Yep.
So where does Boolean satisfiability fit in this hierarchy?
Not really, in a sense. So what you do is Boolean satisfiability actually defines this hierarchy in a sense. You fix the way, so you fix a certain structure of the CNF formulas you're looking at depending on the structure of unbounded ANDs and OR gates in your formula. And then the nesting level of this AND and OR gate, this is basically the number you have here, right? And then the question is there a solution to your input formula of size that takes at most k variables to 1? And this is the sort of parameterized problem you're looking at defining these things. Right? There's also something that corresponds to the whole set, but then it's way beyond this. Right? But it's a little bit, but it's a very good question actually, and I should have mentioned this before really. So this classification is a little bit sort of incomparable to classical complexity. So every problem that can be solved in polynomial time is fixed parameter tractable under any parameterization, because you just ignore the parameter and just solve it. But of course, this running time here really depends on what you take as a parameter. Right? And if the parameter is just the size of the input structure, it just means the problem is computable. Yeah? And if the parameter is just nothing, then you mean just polynomial time. So by choosing the appropriate parameters, you get very different problems and very different complexity types, which are not really reflected in classical complexity, where everything is just part of the input. Right? And so for us, the parameter here will always be the size of the solution you're looking for, or mostly the size of the formula that defines your problem. Right? But sometimes you give some of these graph parameters like tree, but they are defined by a number associated to a graph, and then that will also be part of the parameter. But I'll explain this as we go along. All right, so now basically rephrasing it like this, so you fix your logic like MSO, and then you want to study the class of graphs where the model checking problem becomes FPT. In fact, I'm interested in a little bit more. What I would like to understand really is for any of the natural logics we work with all the time, like FO, MSO, and so on, what would be nice is to identify, to give a precise characterization of the class of graphs where the model checking problem is tractable. Right, so in an ideal world and so on, I'd like to identify a structural property P of classes of graphs, so the model checking problem for L is fixed parameter tractable on C if and only if this class has a property P. Right? Now this is a little bit problematic for many reasons. One is that we've seen that MSO can be, the model checking is in polynomial space, and if that collapses to polynomial time, then it's FPT on every type of graph. Right? So then that program makes no sense. The reverse of this obviously is, if I want to prove that MSO model checking is not FPT in a class of graphs, and that would separate P from P space, which I'm not really aiming for. And so at the very least, we would need to do this under suitable complexity theoretical assumptions, which you'll see tomorrow. But even then, of course, it may not always exist such a precise characterization. There may be gaps, right? So gray areas where we don't know what's going on, and this is reality somehow. You'll see this tomorrow. But I think looking for these sort of as precise as we can get characterizations of tractability for logics will give us real insight into what makes these logics sort of tractable and where we can apply these things. It's just not so easy to prove somehow. All right, I know this is enough introduction after half an hour. Right, so there are two parts of the tutorial. In the first part, so I'll speak, so in this calculation you see here we need upper and lower bounds of tractability results and intractability results. And these are the two parts of the tutorial. The first are upper bounds. where I want to present algorithmic meta theorems or tractability results for model checking problems on specific classes of graphs. And then tomorrow in the second part of the tutorial, you see corresponding lower bounds where we prove intractability results for logics on class. And today, basically, in the first part, in the remaining half an hour or so, it's going to be more survey style. Yeah? So I'll present the basic ideas and methods we use. And then tomorrow, I'll present essentially one result and explain it in more detail so that you see all the combination of techniques really we have to use. All right, so part one, upper bounds. And this is the slide you've seen before. So the same list of sort of all the graph classes and so on. Only now, this is sort of all the results we know at the moment, right? And so MSO1 becomes, except that these should be 1 minus I. Yeah, so MSO2 becomes fixed point tractable unbounded tree width classes, and only here more or less. Yeah. MSO1 is tractable unbounded click width graphs, which is basically on clicks, for instance. Yeah. And then first order logic is up here. So at the moment it is but at locally bounded expansion. I guess most people working there conjecture it to be somewhere here, but it can't go beyond nowhere dense. Right? And this you'll see somewhat later, how this goes. All right, so if you've stayed with me till now, but decided you don't like this so much, and bear with me for 2 more slides, because you'll see all the proofs on 2 slides, more or less. Because everything that we know about algorithmic meta theorems follows a very simple idea, namely, we're given as input the graph G and the formula phi. We want to check whether the formula is true in the graph. And all results basically work by decomposing this graph recursively up to the point where it has only constant size. Yeah. So basically, in the simplest way you can do this, obviously this decomposition can take various forms and so on, and some are easy, some are not. The simplest form is if you're able to split the graph into 2 parts which are nearly disjoint, so they only have a very small intersection, and you can repeat this process recursively up to the point where these things become constant size, then you're basically on a situation of trees, right? And then you can sort of compute wherever you want to compute on these constant size subgraphs, and then combine this to get the full result. And graphs which can be decomposed in this sense up to constant size subgraphs are known as graphs of small tree width. Yeah, and that's the first type of results you'll see. Not every graph can be decomposed as nicely as these things. Sometimes it may be more complicated, but the idea is still the same. Another way of decomposing it, you just cover it by smaller subgraphs, right? I mean, so each of these gray disks here is supposed to be a subgraph, and in principle they should cover the whole graph. I just didn't know how to draw it, right? So we take smaller subgraphs, and the idea, hopefully, they will not only be smaller, they will also have a much simpler structure, right? For instance, if you could show that you can cover your graph by these subgraphs, and these guys have small tree width, then basically you can decompose any of these into constant size subgraphs, and then solve your problem there, combine everything, and so on and so forth, right? Well, this is just very hand wavy, obviously, and this is the other key idea you would use. It's just different forms of how you cover your graph with subgraphs. Well, that's all there is. And so basically what all these results are proved by, they come in 2 components. One is we need a suitable notion of decomposition of graphs, right? Like for tree width, it's a proper separation into nearly disjoint subgraphs, and so on. And then on the logical side, you need the corresponding decomposition or composition theorems for logic, namely that tell you that once you solve your problem on sort of subgraphs you've defined, then you can actually combine them somehow, right? And so if you want to prove any algorithmic meta theorems, then normally you have to prove both parts, right? The separation on the graph theoretical side and the composition theorem for the logic. And this tutorial, I want to focus on the more logical tools here, even though it's a bit cheating, because the difficult part usually comes in the graph decompositions, right? So this is where the deep proofs, and then this is sort of the, well, it's logic, so it's nice and short and more concise if you want, right? But anyway, you'll see what I mean. Right, so the first approach is the composition method, and this is really geared towards graphs which you can decompose into nearly disjoint subgraphs which only have a very small intersection. And basically, if you want to decide whether a formula is true in the union of these, I would like to decompose this into deciding whether formulas are true here, and then combine this. It's a bit of notation I need for this. Yeah, G is a graph and V is just a tuple of vertices, which will normally be the stuff in the intersection. Then by this notation, I just mean the full MSO type of this tuple of vertices in the graph. So the set of all formulas in MSO that are true in the graph at these vertices here. That's way too powerful because it describes the graph up to isomorphism, obviously. So normally we restrict this type up to formulas of certain quantifier rank Q. Yeah? And quantifier rank here means all quantifiers thrown in. So first order, second order, everything. Right? And the same type of definitions for first order logic. Right? And then there's a famous theorem. There's a whole bunch of theorems which sort of people call Pfefferman-Ward style theorems. I think Pfefferman-Ward proved it for disjoint unions, and then there are variations of this, which basically says the following. If you have two graphs, G and H, so this is G and H, and they intersect in this tuple of vertices U, right? Then for every quantifier in Q, the full type of V, U, and W in the complete graph is completely determined by the type U and V have in G, and U and W have in H. Right? So if you know which formulas in monadic second order logic are true on the left-hand side and on the right-hand side, then you can combine this to know which formulas are true in the complete graph. Right? And this is effective. There's an algorithm that computes this type from the previous types in two subgraphs. Right? So that's the composition method we use here. And if you look at this, basically what it suggests is an algorithm, a model checking algorithm on graphs which can be recursively decomposed into subgraphs of constant size. Right? Because obviously the full MSO type of a constant size graph you can just compute, right? It's constant size, you can do anything on it. And then you can use this theorem to combine them to larger graphs and so on, up to the point where you reach everything. And graphs, as I said, graphs that can be decomposed in this sense are known as graph-bounded tree width. And this is the definition. So basically, the tree width is a graph theoretical concept that measures how similar your graph is to being a tree. Yeah. And we say such a graph, which obviously is not a tree because we have cycles here, we say it has tree width at most k if we can cover it by subgraphs of size at most k plus 1. And these subgraphs are then arranged in a tree-like fashion. So this is making it a little bit more precise. These are the 6 actually subgraphs here are used to cover the whole graph, and then we arrange them in a tree-like fashion. Okay, and this here is called a tree decomposition of this graph. To make it a little bit more precise, a tree decomposition of a graph is just a pair consisting of a directed or undirected tree, and for every node of the tree we have what's called the bag. So BT is just a set of vertices of the graph. So the two conditions are satisfied. The first is, if you look at a graph vertex, then the set of bags it's contained in must be non-empty, so every vertex occurs somewhere, and it induces a connected subtree. Yeah? This is the most important condition, actually. And then every edge U and V must be covered by a bag. So both endpoints must occur together in at least one bag in the tree decomposition. And I'll give you an example on the next slide. And then we can define the width of a tree decomposition to be the maximum number of elements in the bag minus 1. And the tree width of a graph is just the minimum width of any of its tree decompositions. So every graph has a tree decomposition. You just take one bag and throw everything in. And so there's also minimum width tree decomposition. And a class of graphs is bounded tree width if there is a constant k. So the tree width of this graph is bounded by k for the tree width of every member of this class is bounded by k. Yeah? So here are a few examples. This is the simplest example where the name comes from. So trees, or more generally forests, have tree width 1, and the tree decomposition is just you take every edge into one bag and then arrange these edges as they are arranged in the tree. Right? And you can show actually acyclic graphs are precisely those graphs with tree width 1, right, which you can arrange in this way. So here's a more interesting example. This graph here, which doesn't really look like a tree at all, but it also has a small width tree decomposition, which you see on the right-hand side. And if you check, what are the conditions on the tree decomposition? Every vertex here must occur somewhere in the bag in the tree decomposition. So take the vertex 1. It occurs here, 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 nearly everywhere actually. Yeah. And it's so certainly non-empty, and it induces a connected subtree, right, which was the second condition we need. And furthermore, that's more complicated to check. Every edge must be covered somewhere, so the edge 311 is covered here, for instance, both endpoints are in. And so what is all this good for? The main, and this is the decisive property of tree decompositions, is if you look at any bag, let's say this one here at the root, and you look at the vertices it contains, then this forms a proper separation in the graph, right? So if you delete these three vertices, 1, 3, and 11, then you disconnect the graph into the left-hand side and the right-hand side, and there's no edge between them. Yeah? And this is exactly what a tree decomposition with all these conditions are meant for, so that this happens. Every bag is a separator in the graph. Yeah? And this is basically the whole thing. If you then think of the Pfefferman and Walzer theorem I just mentioned on the previous slide, what this means is we can, by following the tree decomposition, recursively decompose the graph into constant size subgraphs, which are these bags, and then we are done. Right? So a few more results, and the first who really proved this from the corresponding algorithmic theorem is Bruno Courcelle. He wasn't talking about tree decompositions, but about graph grammars, but it's the same thing. Who showed that if C is a class of bounded tree width, then MSO2 model checking is fixed but intractable. In fact, for every fixed formula, there's a linear time algorithm, a uniform linear time algorithm solving this the model checking problem on the class C. Yeah. And so, in particular, we can do things like three-colorability, Hamiltonian path, and so on in linear time on graphs of small tree width.
You said that you do the decomposition.
Yeah.
At the base level, the size of the graph should be constant.
Yes.
So the game is that you fix the size of this graph before you design your algorithm. It could be size 4, 5, whatever, right?
Yes. This is the tree width. Yeah.
And that doesn't figure in the parameter over here.
No, you're right. It's an odd way of writing this theorem, actually. No, it's not odd. It's just so we fix a class C of bounded tree width. So that fixes you. That gives you the. Actually, it's a perfect question because I'll explain later. So what the real parameterization you could use is the input is your graph G in C and the formula phi in MSO. And you could take as parameter just the tree width of the graph G plus the size of the formula, right? And that problem is fixed but intractable, right? The question then is obviously C models. Now here in this formulation, we fix sort of the uniform bound for the tree width, which is given here. Yeah, so it's slightly less. This is more. This is even stronger than this one, if you like. Yeah. You know, it also solved my dilemma because Jan put me into trouble this morning when he said it was heresy not to use the blackboard here, and I had nothing to write on the blackboard today, so it's.
But you still have to get a tree decomposition.
There's more coming now on the next slide. Maybe I just go through the proof quickly, and then if there are more questions, we can answer. So this is a theorem I'd like to prove. I'm running a little late. So one problem is that deciding the tree width of a graph is NP. The problem deciding the tree width or computing the tree width of a graph is NP-complete itself. So somewhere we are reducing an NP-complete problem like Hamiltonicity, another NP-complete problem computing the tree decompositions. But then Boatlander proved that there is an algorithm that computes optimal tree decomposition and it runs in time exponential in the tree width, but only linear in the size of the graph, right? And this is the running time, obviously, we are looking for. And so if C is a class of graphs that has a bound k on the tree width of its members, then this becomes a linear time algorithm computing optimal tree decompositions on C. Yeah. So that's the first ingredient we need. The second ingredient is the one you've seen, that if you know the type of this tuple on the left-hand side, on the right-hand side, we can combine it effectively into the type of view in the whole graph. And then that's all we need to show the theorem. Basically, if you give me a graph of tree with MSO k and fixed MSO formula phi of quantifier rank q, the first thing I do is I compute the tree decomposition of optimal width using Boatlander's algorithm in linear time. Then I compute the MSO q type of all the leaves. So I compute the MSO q type of this bag and so on, and here. And then sort of I go bottom up, right? If I know the type of these two subgraphs, then I can compute using the Pfefferman-Wald theorem the MSO q type of the subgraph induced by the vertices in here. Yeah. I do the same on the right-hand side, and this way I work my way up, basically. And of course, once I've computed the full MSOQ type of the root, so everything in the whole graph, then I can just check whether phi occurs in it or not. Yeah. And this
So the complexity is much worse than you need to do, right? Doing it this way.
Well, it depends on how fine-grained you want your analysis. That's what's here. Because there's no algorithm. So the complexity is basically non-elementary in the size of the formula because the types go very quickly. But you can't do much better. So what Freck and Grohe proved, unless P equals NP, there's no FBT algorithm for MSO model checking on even trees that only has an elementary parameter dependence. Yeah? And unless FBT is the same as W1, so in parameterized complexity, the same holds for first order model checking. Yeah?
But the point is that in some sense, your algorithm described is always going to be non-elemental.
Yeah. No, it's true. I mean, this is not the best algorithm. This is the automata.
It's the worst algorithm.
It's a one-slide proof. I mean, that's good.
Yeah, exactly. It's not the worst. It's a short proof. Yes. Now, this is basically the automata theoretic approach, and you turn this into the automaton if you want, and then the automaton would have a state for every possible type, and then you let it run on the tree decomposition. In fact, for many years we were speaking about this problem and saying, look, this is a theoretical result because the parameter dependence is so high. And then to graph algorithms, people actually from Aachen, Peter Osmanin and his students, they just went on and implemented Cosell's algorithm. They didn't do the sort of type-based approach. They did a more clever sort of algorithm engineering approach, and this works fantastic. So I've seen this running. They can do formulas like, I've seen examples where they use computing minimal dominating sets and all these kind of things, and it runs extremely well. In fact, they did a complexity analysis of their algorithm implementing Cosell's theorem, and for problems like dominating set, they get up to the optimal bound you can have in parameterized complexity. So it's not as inefficient as we thought. And I guess the right way of just stating the parameter dependence is just MSO can encode very difficult problems in extremely short sentences. But this is not what, and this is what's behind here. So they encode sort of propositional satisfiability in extremely concise sentences, and then you can't have better parameter dependence. But of course, that's not what we do. Right? What we do is you want to compute a Hamiltonian path, or you write the formula that computes it, and this can be solved very efficiently.
No, but the issue is not with Cosell theorem. The issue is the algorithm, the proof that you described that does by computing the type. That's
That's terrible. Yes.
Complexity.
Yeah.
They don't do that.
No, they don't do it, but they take about 30 pages to prove it, and I take about one slide. No, they're better, like always. I mean, they're much better algorithms and proofs and so on. It just, yeah. So there we go, right? Yeah. But it's a good point. I mean, if you really, but this goes for all the algorithm eta theorems. I mean, as I present them, they're purely theoretical results. They will all be not elementary. They will all be horrible. If you really want to implement them, then you have to do a lot more algorithms engineering. You can do this, and they showed this that this works. But it's significant work that goes into it, and it took them, I think, 3 years to develop it to the point where they sort of can show this openly. Anyway, I'm running extremely late now. I should hurry up a little bit. Unless our second speaker hasn't showed up yet, then I can just prattle on for another half an hour. Okay, I'll speak till it comes up, let's say. All right, so this is so what we've seen here is basically MSO2 unbounded tree with graphs, and I won't go to MSO1 and click with because it's not so nice concept. What I would like to do is to show you how these results are proved, basically. So we now go to first order logic, and we start on bounded degree graphs because it's easy, and then the same proof will go through for quite a few of these classes here. Right? And this is the second type of sort of decomposition I mentioned in the beginning, where we can't really decompose the graphs entirely into disjoint parts anymore, but we can cover them by very simple subgraphs. And the corresponding logical method you need is Greiffman's locality theorem, and a bit notation here. So G is a graph, say the Greiffman graph of a structure, or just a graph if you don't know what the Greiffman graph is. Then the distance, by this here I mean the distance between two vertices U and V in the graph G, so the length of the shortest path between them. And by nr of v, I mean the r neighborhood of a vertex v in the graph. So the set of vertices of distance at most r around this vertex v, everything that's close to it. And now I can define first of the formula phi with a free variable x to be r local for some value of r. If every graph G and every vertex in the graph G, the formula is true at the vertex in the whole graph if and only if it's true at the vertex in the R neighborhood around this vertex, right? So in the subgraph induced by the R neighborhood. So whether the formula is true only depends on everything that's very close to V. And whatever the rest of the graph does, it doesn't really matter. Yeah? That's of course a very restrictive form of formulas, but what Greifman proved is that every first order sentence is equivalent to a Boolean combination of what's called basic local sentences, and these are sentences of this form here. They say, I have m elements, the distance between any pair of them is very large, so at least 2r, and then locally around each xi, an r local first order formula psi is true, right? And this is a constructive proof. So basically all we have to find is we have to choose very far apart vertices and then decide something that's only close around them, right? And because the distance here is at least 2r, it means the r neighborhoods around 2xi and xj do not overlap, and we can consider them separately. That's the importance of this distance here. Greifman's proof is constructive, and before Moshe asks again, it's not extremely efficient, let's say. So we looked at how large these formulas in Greifman normal form. So this is called the Greifman normal form, Boolean combination of these things. And again, transforming a formula into Greifman normal form, it grows non-elementary. Yeah. And so basically, all the results based on Greifman's locality theorem will have non-elementary parameter dependence. Yeah. Probably you can do better, but we didn't try. Yeah. And now maybe let me give. I'm afraid it looks like my successor has come. So in the last 6 or so minutes, I'll just present the following theorem, and then we take it up tomorrow. So the theorem I want to prove that goes back to Detlef Caesar, even though I'm presenting a proof by Grohe and Frick, is the following. So let C be a class of maximum degree at most D, so no vertex has more than D neighbors. Then I want to show that the first order model checking problem on C is fixed parameter tractable, and the parameter here is just the size of the formula, but we fix the degree. Yeah, so it's the same situation as you asked before. Right? So that's basically on the outside. And so, so how does it work? Well, the first is we are given this formula phi. So by Greifman's theorem, as it's constructive, we can translate it into a Boolean combination of basic local sentences. And hence, all we have to do really is to be able to check these basic local sentences. Yeah? And psi here will be an R local formula around the variable x. And once we can check truth of these, obviously we can check Boolean combinations and so on. So this is what we have to do. Yeah? And this is how it works. So if G is a graph maximum degree D, if that formula here is true in the graph, then what we have to find are m different vertices, which are pairwise far apart. And locally around each of these vertices, that formula psi here must be true, which is an R local formula. Yeah? And because the distance is so large as such, these neighborhoods do not overlap. Right? And so this is what we do. In the first step, we go through all vertices of the graph. We compute its R neighborhood, and then just check whether the R neighborhood satisfies the local formula psi. But since we are working in a bounded degree graph, the R neighborhood of any vertex is just constant size. Right? It's D to the R, basically. And so this is constant size neighborhoods. We can just check this any brute force. Yeah? And if a vertex B, its neighborhood satisfies the formula psi, we color it red. Yeah? And this is running time linear in the size of the vertices. Yeah? So there we go. After the first step, we are left with a graph G and a couple of red vertices. And now what we have to find here, basically, as I said, this is all linear time. Yeah? What we have to find here is whether we can take m red vertices, which are pairwise far apart, right? And then we know that the basic local sentence is satisfied. And this we do by a greedy approach. So we just start with the empty set of red vertices, and as long as we haven't found enough of them, so Q is the set of red vertices. We just pick a red vertex, like this one. Suppose we want to find 4 of them. We add it to the set L of vertices we found, and we delete every other red vertex that's too close to it. Right? That would be in the R neighborhood. And we continue. So we take the second one, and then we can take the third one. And now there are no more red vertices left, right? But we have only found 3 of them, and we are looking for 4. Right? Now, if in this greedy approach we find 4 red vertices, we are happy and we stop. Right? If we don't find 4 vertices but only 3, like in this case, then we know that every red vertex must be close to at least one of them. Right? So basically, what we can do is we throw away the rest of the graph. Yeah, we just keep the R neighborhoods of the 3 vertices we found, and we are guaranteed that they contain every red vertex. But now this is again a constant size subgraph, and so we can check first order formula, just ask for are there m different red vertices which are pairwise far apart. Yeah. Or because it's constant size, of course, you can just do it by hand if you want. Yeah. And so then basically by checking this formula here in the unit of these neighborhoods, we can determine whether we have found sufficiently many red vertices. Yeah. And again, the running time of this is just linear time. Yeah. And so this proves this theorem here, and maybe in the final 2 minutes that I've got, let us analyze this proof. So where did we actually use the fact that we had bounded degree, right? Because we are showing much more than we had to show. Well, we used it at 2 points. So one here, we computed the R neighborhood around the vertex, and then in that R neighborhood, we just checked an R local formula. And here, because it was constant size, we could do this. Right? So that's one point where we need the bounded degree property. The second type is here. Once the greedy approach failed to produce sufficiently many red vertices, we threw away the rest of the graph and just checked this formula here, which is again a first order formula saying there are m different vertices far apart in the union of these neighborhoods, which is again by bounded degree constant size. But this is all. So basically the whole algorithm relies on the fact, and the only way we use bounded degree is that in our neighborhoods around some tuple, we can check first order formula sufficiently, right? And as soon as we can do this, the whole proof goes through for any class of graphs, right? And here all this radius and so on, and we use all depends on the size of the formula and hence only on the parameter, and we are happy. And so more generally, what we can prove, and this is nearly my final slide and here for today, is the following. What this algorithm shows is if the following problem is fixed point attractable, namely you give a first order formula and a graph, and you have a few vertices and the radius R, you want to check whether the first order formula is true in the R neighborhood of these vertices. If you can do this in FPT time by a parameterized algorithm, then the same proof as before shows that first order model checking is fixed point attractable on the whole class of graphs C. Yeah? And that's a generic statement basically. So if you want to prove something, if you can establish such a theorem here for a class of graphs, then you can get tractability for the complete graph of graphs. And so the bottom line of this is for efficient first order model checking, it doesn't have to be the case that the complete graph is somehow structurally well behaved. It only has to be the case that every neighborhood is somehow nice. Yeah? For instance, not the whole graph needs to have small tree width, but sort of only the neighborhood needs to have small tree width. Yeah, and this is and this is what's known as bounded local tree width, or this gives rise to the idea of defining bounded local tree width, where for every graph G, the local tree width is defined as a function that associates to every radius R the maximum tree width of an R neighborhood you would find in the graph. Yeah, this is the last slide, if that's all right. It's 1 minute even less. Yeah. So class C of course is bounded local tree width if there is any function from n to m that dominates the local tree width of all of its members, which means neighborhoods in graphs in this class the tree width doesn't grow too quickly with the radius. Yeah. And prominent examples obviously are the class of graphs of bounded degree, as we've seen, because a constant size graph can only have constant size tree width depending on the radius. Another, the most prominent example is the class of planar graphs. By a theorem by Baker, a planar graph of diameter r has only tree width 3 times r. Yeah? And so the tree width is grows linear in the size of the neighborhoods. And so the result we've seen before, basically the same proof, and this is how Frick and co. actually developed this proof, shows that first order model checking is FPT on planar graphs, graphs of locally bounded tree width, and so on and so forth. And I'm over time now, I'm sorry. I'll conclude here for today, and we continue tomorrow morning. So thanks very much.
Question?
said something about MSO2 is really guarded second order logic. Can you say a little more about that?
Well, guarded second order logic means basically you can quantify over arbitrary relations if you want, but then there's a guarded first order formula behind it. And or another way of expressing this is you can quantify over guarded relations, which means if you want to quantify over a 3-array relation, then every 3 tuple in the relation has to occur together somewhere in another relation in the graph. Right? Which means if all you have are edges, the only thing you can quantify in guarded second order logic is sets of edges, basically. And this is exactly MSO2. But guarded second order logic is defined for arbitrary relational structures, so you can go much beyond, except we have now, you can go to the Greifman graph and define its tree width there, and then this is the same thing.
What general theorem you can say about guarded second order logic?
Guarded second order logic is fixed point retractable on any class C of relational structures of bounded tree width. And the tree width is the tree width of the Greifman graph. But you're not actually gaining so much. I mean, it's not that there's super new sort of insights in this, right? Because
But this sounds like it should be more explicit than MSO2.
on graphs it's not, because it's the same thing. Yeah, but
you can deal with arbitrary
yes,
structure.
yes. So basically, the idea of defining MSO2 is really the idea of defining guarded second order logic. I mean, the thing you want to avoid, basically, if you have a graph, you want to avoid quantifying over set. You want to avoid adding new edges somehow, right? Because if the tree width is small, then you don't want to sort of adding new edges that destroy this property. Or in a relational structure, you don't want to add really new relations. You just want to quantify over subsets of things that are already related. And this is what guarded second order logic is, because in that way you don't destroy structural properties of the structure.
Related to this, you could also think of relational structures encoded in the incidence form, where you have a vertex for every tuple and a vertex for every vertex.
Yeah.
Incidence relation.
Yes.
That would be the same as guarded.
Yeah. That would be the same as guarded, yes.
Okay. If there are no more questions, thanks, Stephan, again.
Thank you.